This call is now being recorded.
Yeah, by the way, Arundhati, are you there were you there last time?
Sir, actually, I was trying to adjust the volume of my laptop and it got muted. Couldn't hear anything for a minute. Then my friends told me that you were calling.
You were not there, right?
No, sir.
Yeah, so in online class, it is difficult for teacher to know who is there or not. So, so I'll ask sometimes some small questions to see if those people are there and attentive or not. Just like you have seen in school time. And that, of course, doesn't mean create an impression or whatever, but it's just to make sure people are involved. All right, so today is 21. So last time we were discussing about smooth functions, right? So our topic is smooth maps, right? Smooth maps. Actually, we want to define smooth maps between two manifolds. That is the idea. That is our aim, actually. So last time we discussed what we mean by smooth functions. So can you remind me, anybody, what is a smooth function from a manifold M to R? You know, the notation here, I mean, the concepts here are a little bit non-standard in some sense, that whatever you have seen till now, you've seen smooth or differentiable means in some sense by using limits, right? But in this case, there is no limit. So here we define in terms of what already known in Rn. So that is the reason. So I hope some of you have seen the notes. So can you tell me what is a smooth function? So you have a manifold M here and a function to R. When should I say this F would be? Let's say fix a point also, P. When should I say F is smooth at the point P? Smooth means infinity, but one can define C1, C2, C3, everything. But
It's a manifold with a differentiable structure, so we can consider that case. So there will be a open set surrounding P.
Yeah.
And a map which homeomorphically maps that open set to an open set in Rn. So let that be psi. Then we consider F composition psi inverse, which will be mapped from Rn to R. If that is smooth, we call it smooth.
Right. So M, since M is a manifold, so it has a differentiable structure. In terms of what I said, looking at an atlas is enough. Right. In a differentiable structure, you might have several open sets like this, right? The point is containing P. You are not going to go to check everybody. You just want to check one. And by remark I made earlier, that actually this is good enough. All right. So the point is here M. So M, since M is a manifold, it has an atlas, or it has a differentiable structure. So you take an atlas in the differentiable structure, and you consider this. So this, let's say this is U, and this is phi. And now this phi goes to, if M is of dimension n, it goes to some open subset of Rn. So this is actually phi U, which subset open in Rn. Now this is the map you should be looking at, F compose phi inverse. So F is, the fact is the following, or the definition is the following: F is said to be smooth at P if for some chart U phi. Charts for some chart means chart in the differentiable structure. F compose phi inverse from phi U to R is C infinity smooth. Okay. So C infinity and smooth, I'll use it interchangeably, and they will mean the same thing. All right. So keep remember, do remember this fact that. So this one, you do remember. So by smoothness, we mean actually we go back to Rn locally and see the map, whatever we are considering, composed with that chart map inverse is smooth. And if it happens for every p, then we'll say speed is smooth in smooth map on M. Right? If F is C infinity at every point P in M, then we say that F is a smooth function on M. All right. So smooth function from M to R is perfectly makes sense. It does perfectly make sense. Now, what do we want to consider as follows? So this is what we are discussing. Smooth maps. These are actually the basic part of this course. If somebody misses out here, understanding what is smooth maps, he or she will be in deep trouble later on. So it will be used almost every lecture next time onwards, even this time onwards. So we want to show smooth maps between manifolds. That's what we. Oh, so before that, let me write a proposition as 2 does. As theorem, so what it, yeah, it's called as proposition. So let me call it that same. So what I want is to just mention that smooth, for the smoothness, you don't need to check for all the open sets. What you need to check is for an atlas. So this is, let M be a smooth manifold of dimension n, a, and let's say F f from M to R be a function, then the following are equivalent. 1. F is C infinity on M. Second thing is, for an atlas F so contained in the differentiable structure such that F compose phi inverse is C infinity for every chart U phi in F. For every chart V psi of in the differentiable structure, in the differentiable structure F compose for psi inverse is smooth or C infinity. Yeah. So this is what my point was, even for the last when I talked last time also. So what I said, that it is good enough to see only one atlas, one atlas, and look at the charts on that atlas and look at this composition. Because if you consider three, then you have to check a lot of things. So for every chart in a differentiable structure, and differentiable structure is uncountable. There are uncountably many things. So I mean, checking that will be difficult, and that is why, to show smoothness, it is enough to look at this one. We will look at later. Uh, I mean, the equivalence of smoothness in terms of coordinates. So this chart maps are nice. They actually gives the coordinates in the manifold. So in the manifold, it's not Rn, right? It just doesn't have coordinate x1, x2, xn. But by the chart map, you can pull back the projections, right? I mean, I'll say what pullback means in shortly. So, and those we will call as coordinate functions. So we'll get coordinate x1, x2, xn in the manifold, and we can do the partial derivatives, everything. The notion of partial derivatives will be there. Yeah, any question? So proof is very simple. Already I have discussed in the last class. Any question? Okay. So next.
So in the proposition, like the third statement, we defined one like that, right?
Just a minute, let me go back. Oops, sorry. Yeah. Sorry. Where was it? It is like this. Yeah. So, yeah, third statement we have defined in this way. Yes.
So I mean, we defined f is C infinity. Like the definition is the third statement.
Yeah, definition is, that's why I mean it's equivalent. So
Sir, I
I
think
mean,
the third statement says
not even
if
that. Definition was, I mean, for every p. So you look. Let us go back and look at definition. So here, what I said, for every p there exists one chart in the differentiable structure, right? Definition is little bit different than those three. So there exists one chart around you, right? Said to be smooth if for some chart. You see? Where is?
Yes.
See?
Last class, I think you defined for every chart.
Really? Let me see. Yeah, this is the good thing about using Google. So this one, right? Yeah. Well, last time, when was it? 19, is it? Not this one. Maybe this one. Yeah. Yeah, right. Oh, yeah, okay. So I said for every, right? Hmm. Yeah. That is correct. So in the yeah. Right. Yeah. So you can consider last one as definition or this one as definition around P. So there is no problem. So it says this. Of course, f is infinity. Yeah. Right. Third one is third one you can consider definition. So what it actually says is nothing but you can consider an atlas instead of looking at everything. But the point is, I mean, well, so and in a differentiable structure. So think of this way. So you have a manifold, and around each p you get a chart, right? You get a chart. So let me give you what I said here is not very different from what I said last. What this one is. So I'm keep on rewriting. So these are all equivalent. So you can think of one. So now let's look at, for every point there exists one chart. Okay, in the differentiable structure, such that F composed P inverse is smooth. Now, can you get me an atlas from there?
You can consider all those charts around each point.
Right, around every point there exists one chart. So consider all those charts. Take the union. And take the collection of the all those charts.
Yes.
Right, it will cover M, and that is the only thing it is. I mean, it was needed to be an atlas, right?
it should be
So
compatible.
I mean, you are already working in a differentiable structure, so everything is compatible. We are not going out, so we are not inside. I mean, we are not outside of a differentiable structure. So you are working in a differentiable structure. When you define, your mind should be concentrated within a differentiable structure, right? So everything is compatible. Whatever open set you choose from there, and charts are and maps which gives you charts, those are always compatible. So smoothness, the definition of smoothness is dependent on the differentiable structure. It might not be dependent on the charts in the differentiable structure, but it depends on the differentiable structures. All right. So this incompatibility part is not there in the definition of a smooth function, because you are, so let's say, I mean something you can do if you are inside a house, and this inside house is inside the differentiable structure. So you can define smoothness once you are inside in a differentiable structure. If you go out, you don't know what smooth is. Okay, you pick a different house, you look at that is a differentiable, that might be a different differentiable structure, and you get functions different. All right, does it make sense? Okay, so next one. Okay, so before going back, so I was keep on saying what is pullback, and so let me define that. What I mean by pullback. So pullback is a notion. I think it's new notion to you. So suppose what is happening? Suppose capital F is a map from M to N, where M and N are manifolds. I mean smooth manifolds. So manifolds, we mean smooth manifolds here. So unless I say that it is topological manifold or something, it will always be smooth. Now if, let's say, f is a function from N to R, then you can define the pullback of f by capital F is denoted by f star f, and it is defined by f star f is f compose f, right? So this f star f f star f is a map from M to R. All right. So this is composition, but somehow this pullback thing is quite a bit used in differential geometry, and it's not just for the function, it is composition. For different other notions, it might not be composition. So a different notion makes sense. All right. Now we define smoothness, smooth map between manifold. Yes. Border pore. Right, manifolds means smooth manifold here. So suppose capital F from M, well, we consider first, let M and N be smooth manifolds of dimension M and N respectively. A continuous function capital F from M to N is said to be smooth if what should I say, for every or for there exist, or well, smooth, let's say at P. Let us define at a point at P in M if there exist there exist charts U phi at P and V psi at F of P such that F compose phi inverse, then compose psi from. So what does this map will be? Yeah. So phi of U intersection F inverse V to Rn is C infinity smooth. Does it make sense? Well, let's look at the picture. That might help you to understand it. So you have here an M, and here you have N, and you have the map capital F. All right. Now, what do you look at? So suppose P is here. You look at a chart around P. This is U, right? And P goes to FP here. So look at a chart around FP also. This is called V. Now chart means you have map also. This is psi goes to inside Rn, some open subset of Rn. And here also you have the chart P, it goes to Pu, which is open in Rm. All right, because M is of dimension M and N is of dimension N. That we have taken for this definition, right? And what you want? You want this one. So maybe let me put a different color here. So for smoothness, you want this map to be smooth. So this is the map. And of course, see here, it is psi is defined on V only. So the F inverse, if it does not contain properly U, you need to intersect. And that is why we have taken U intersection F inverse V. And F is chosen to be continuous, so F inverse V is open. All right. So this map is F compose phi inverse compose psi. So this F is smooth if this is smooth. All right. Does this smoothness make sense to you guys? Yeah. Any question here?
Sir, can you go back one page?
Yeah, sure. So I mean this one?
Okay. I actually thought it was okay. It's clear. Sorry.
Yeah, so this is around each point P. So now you say, so continue definition, a continuous map F from M to N is said to be smooth if F is C infinity. Well, yeah, smooth at every point. Smooth at every point. Of M. All right. Any other question? Okay, an example. So take N to be the manifold N to be R N, let's say, right? So if M to R N, so when we say this map is smooth, so this N to be R N and chart or an chart a chart Rn identity, right? So here in this case, it would be here identity all the time goes to Rn, and here for every point you have this phi, right? So this composition is F compose phi inverse. So here this AP this so this a continuous map is smooth if F compose phi inverse is C infinity, right? And this here, this you can do again for its atlas or for every chart, doesn't matter. So C infinity for every chart in an atlas. That is actually, so whenever I mean you would think a smooth map, you would think that you have an atlas and there or every point has a neighborhood which you can think of as coordinate neighborhood, which means you have a chart map from there, and that would be the inverse, this F compose phi inverse to be is smooth for such things. So that should be going on in your mind when you think about smooth map. So now, of course, if you take M to be Rm, the usual smooth maps will come. So if M is Rm, then the usual smooth maps appears. If N is 1, we recover the smooth functions. All right. So this is kind of course, it's half example. So if M is Rm, you get the usual smooth maps in calculus. And here from Fm to R, so we have generalized that generalized the smooth function from M to R for between smooth maps between two manifolds. All right. Now, so this is again true now. I mean, whether for every point you have a one chart or you can do it for every chart in a differentiable structure. So let me write it as proposition, but yeah, you can prove it yourself. Suppose let me divide this board. Suppose f from m to n is C infinity, then for every chart u phi of m, so here m is already contained in differentiable m contains, well, m with a differentiable structure, and for every chart p comma psi of n, f compose psi compose here phi inverse is C infinity. All right. So once you define as for every point there exists one chart where this composition is smooth, then you get every chart. And proof is same. So the proof is exercise. So you have nothing. So you need just to convince yourself that whether you consider every chart or whether you consider one chart, it's enough. It's equivalent. Around 1 point. So around 1 point, one chart. Or around 1 point, there might be uncountably many charts. So at that point lies. So this to checking psi compose, f compose, phi inverse, checking one or checking this uncountably many is kind of equivalent. All right. Any question here?
Sir, when we say every chart, we mean charts from the chosen differentiable structure, right?
Oh, yeah. I mean, smoothness you can define only, I mean, whenever you say this M and N are manifold, already contain in differentiable structure for M and N as well. Without having that differentiable structure, and you don't go beyond this chart. Whenever you say these charts, you don't go beyond that differentiable structure. Okay. All right. So again, like functions, one can have three equivalent conditions. So if m to n is C infinity, or it is for every chart given two atlases, you have this C infinityness of this composition, or given every chart, as we said last time in the last proposition, that the composition map is C infinity. So let me just state this again. So there is nothing to prove here also. Oh, sorry, proposition. So let M and N be two smooth manifolds and F from M to N continuous map. So this continuity I have not talked about when we talked about functions, right? So you can think Why didn't I talk about continuous map? So then the following are equivalent. One, F is C infinity. Secondly, there are atlases F1 on M. I mean, inside, of course, inside the differentiable structure. And F2 on N such that psi compose F compose phi inverse is C infinity for every charts U phi in F1 and V psi in F2. So this F1 and F2 are inside the differentiable structure that we consider saying this to our smooth manifold. And third thing is psi compose F compose phi inverse is C infinity for every charts U phi on M and V psi on N. So there, this composition here means for every charts in the differentiable structure for M as well as for N. Now, in some cases, this might not be defined, right? This might not be defined. So here, under the assumption that wherever it is defined, right, this composition might not make sense in some charts, right? Yeah, any question here? Okay. So this is also the proof is easy. So I'm not going into the proof. So these proofs are actually interesting question for this quizzes. So these proofs are very simple. So proof is an exercise. Already discussed. Everything is there. So the main idea here, let me say what is main idea. So there is one thing. So if you compose this, let's say psi compose F compose phi inverse. So what you need to write with properly in a different chart, combining with a different chart, what you need to write is as follows. This so here is the fact. This is C infinity. This should be if and only if the following. So you look at another psi, I mean phi alpha and psi beta. So let's say U alpha, phi alpha, and U beta, B beta, psi beta. B beta, psi beta. These are two different things. So here, what you need to write. So if it is this is C infinity, then you can write this one. Psi alpha compose F compose phi alpha inverse is C infinity. So if you look at two different charts or other charts. So what you need to write this one as psi alpha compose psi inverse compose psi compose F compose phi inverse compose phi alpha inverse. So this is smooth, this is smooth, this is also smooth, and these are all defined in certain open subsets of Rn, right? So this is it. So algebraically, this is it. You need to make sense of the proper domain, but this is, since it is for every chart in an atlas, things are happening, so you can actually cover the whole of it. So if you take other charts and fix a point, take other chart on that, you can actually look at this psi alpha compose F compose P alpha P. I wrote beta, right? So let me not go beta, so put it alpha. Yeah. So this is the thing. So this is C infinity, this is also C infinity, this is also C infinity. So the composition of C infinity maps in Cn, Rn is C infinity. That's it. So this is the idea of the proof. Now your job is to write things properly. All right, so now proposition. So as we did for Rn, composition of two smooth map is smooth, right? So here also, so if F from M to N and G from N to P be two C infinity maps, of course M and P are manifolds. So suppose, let me write that M and P manifolds. If these two are smooth map, then the composition, right? G compose F from M to P is C infinity. Any idea of this proof? This proof is also simple. Any idea? Yeah, any idea how to prove it? So suppose here this is M, this is N, and this is P. All right, here it is F, here it is G. Now you need to look at the composition. So first of all, F and G are continuous. Composition of continuous map is continuous, right? So continuity of F compose G is trivial. So what we need to look at? This map. this map, right? This map, which is G compose F. Now, what do you mean by smoothness of G compose F? So you fix a point here. So fix a point here. Let around 1 point. Let's say this is A. So around this point you have a chart U, and this is Phi. And here Fg compose F of P. So call this C, which is G of F of A. And here let's call it F of A, which is B. Okay. Now around this point C, there is another chart. There should be a chart V. Let's call it W. Call it W. Now we want, so by definition we want this one to be smooth. This one, this is let's say phi psi. Let us call it sigma. So this map, this goes to some open subset of, let's say, R M, and here it goes open subset of some RP. So this map, this is G compose F, and here compose sigma. Here compose phi inverse, and here compose sigma. Does it make sense? We want to show this is smooth. This is C infinity. Make sense? Is the picture clear to everybody? If you have any question, you can ask. All right. So how to show this? We consider around this point B a chart. Let's call it V and call this map psi. It goes to some, let's say, R N. Now what you do, you break this map coming from here and then going back. All right. So what do you want? How to show is the following. You break this yellow map into two parts, going here and then going from here to here. All right. Now this blue map is what? This blue map is F compose phi inverse compose psi, right? This blue map, and this part of the blue map is G compose psi inverse compose sigma, right? Now what is this? This is composition, right? So this and this is composition. So what happens if you compose it, right? So sigma compose G compose psi inverse compose psi compose F compose phi inverse. This is nothing but sigma compose F compose G compose phi inverse. All right. So hence composition of two smooth map is smooth. Hence this is smooth. Is the proof clear? So this is the proof. Is this proof clear? Pictorial proof clear? There is nothing else. Taking one chart is good enough. You look at one chart. Yeah, is the proof clear? Okay, so what next thing is, let me define what is called diffeomorphism. So diffeomorphism between two manifolds. So all the topics you'll find in Tu's book. So a diffeomorphism F from two manifolds M and N is a bijective C infinity map whose inverse is also C infinity. Just an example, and then we'll leave. So an example. So consider R with identity, okay, and R with phi, right, where phi x is equal to x cube. Sorry, phi x equal to x to the power 1/3. Sorry, x cube is fine. This is x cube, and this is capital F. So capital F x is x to the power 1/3. Sorry, 1/3. Right? So F is a bijective map. Yeah? This is fine. So F is a bijective map.
Sir, we have another class and it is started.
Okay. Just 1 minute. Bijective map. Yeah, I'm sorry. We are just. Yeah, so F is a bijective map, and actually F is here a diffeomorphism. So that we'll check next time. Yeah. Okay. Okay. So we'll leave here.